Okay, in this video we are gonna continue these lessons about Unit 5, and we will talk about stellar classification, by which we mean the out there in our galaxy and in other galaxies there are many different types of stars. One of them is our sun, of course, but as we will see, there are many different types of stars, and for each type of star, there are many stages in the evolution of a star, including its birth, its death, and so on. And by the way, please let me know whether the quality of these videos has improved, because this is the first video I'm recording with a Bluetooth mic that I bought for these videos, and yeah, I'm hoping that there will be better noise cancellation and so on. So let's write down a few things. So stars can be classified according to the light they emit. To the light they emit. And by this, by light they emit, we mostly mean its luminosity, okay? Luminosity. Is it with a C? I think it's with a C. So before we talk about the light they emit, I want to remind you about emission and absorption spectra, which are important to understand what's going on. So let's write this down as a quick recap. Emission and absorption spectra. All right, so let's start with emission spectra, okay? Emission spectra can only be observed when you have isolated atoms and there are electrons jumping in excited orbitals, and then they return back to the ground state and so on. I mean, I'm just giving you a broad overview. What I'm trying to say is that you cannot observe the emission spectrum of iron in an iron rod. That's impossible because you have as many atoms in that piece of metal as Avogadro's number, okay? And because each atom has its own levels, levels interact, atoms interact with each other, etc. So the whole thing is ruined. The only way to observe emission spectra is through gases, okay? Because in gases you have isolated atoms and they don't interact with each other. And yeah, that's why you see emission spectra. So in gases, let's write this down. In gases, there are isolated atoms. Oops. There are isolated atoms. Remember, this was the requirement we demanded when we talked about the ideal gas law. We demanded that atoms are isolated and they don't interact with each other in gases, okay? So yeah, in gases you can observe emission spectra. So in gases there are isolated atoms, comma, and electrons orbit around the atom in quantized orbitals. Okay, so what do we mean by that? Let's make a quick scheme. So let's say we have a positive nucleus in the middle. We don't know which atom is this. Maybe it's helium, maybe it's hydrogen, maybe it's neon. Anyway, it doesn't matter. All it matters is that the electrons can only exist in these orbitals. And by quantized, we mean A quantity is quantized when it's discrete, like when it takes discrete numbers, 1, 2, 3, 4, 5. So you see how electrons here only exist in these two orbitals, the first one and the second one, okay? So, and maybe there is a third one, which is unoccupied over there. So if an electron jumps to this orbital, so let's call this 1, 2, and 3. So if an electron jumps from orbital 3 to orbital 2, it does so by emitting a photon with energy h times its frequency, and this quantity h times its frequency is equal to the energy. I don't know why that red line appeared. Let's see. Okay, that went away. Okay, the energy of the photon is equal to the energy difference between, so basically this is E3 minus E2, where E3 is the energy the electron has in orbital 3, and E2 is the energy the electron has in orbital 2, okay? And yeah, this is all I had to say here. Let's write this down. When electrons are excited to higher energy levels, they return back to the level they started, or in other orbitals. It doesn't have to be the level they started, okay? Or in other orbitals by emitting light or electromagnetic radiation. Okay, so delta E is h times the frequency, and because the speed of light is equal to the wavelength of the electromagnetic radiation times the frequency, then if we combine these two, we can also have the relationship delta E is equal to h times the speed of light over lambda, okay? So when we have a gas, maybe in a discharge tube, so a discharge tube is a tube containing some gas that is at a low pressure and density, and you apply some electricity through this tube, and the electricity makes the atoms get excited to different energy levels, etc., and then you get light out of that. So this light, when we have a gas that is excited and then it gets de-excited, I'm sorry. So this light will be discrete. Actually, it's better to say this light will appear as discrete lines in the spectrum. Okay, so what we will observe is if we have this discharge tube and we rotate it around and we observe all the types of light it emits, you will see something like this. Okay, you will see maybe a red line, then close to that, actually, is it the other way around? So the longer wavelength, I think, yes, I think the longer wavelength will appear over here. Let me quickly check. Yes, okay, so the longer wavelength will be all the way to the right, then a shorter wavelength will be there, and maybe yet another wavelength will be there. The blue has the shortest wavelength, it's the most energetic, so it's going to appear to the left. Okay, so this is an emission spectrum. Okay, discrete lines, beautiful, etc. Now let's go see what an absorption spectrum is. So if light emitted by atoms again, okay, so maybe we're dealing with a star, okay, so if light emitted by atoms passes through some gas material, and the gas material emits a continuous spectrum, then the light that corresponds to a certain electron jump will get absorbed and appear as a dark line in the absorption spectrum. And to understand this, imagine that you have a hydrogen gas, okay? Hydrogen that emits some lines that are discrete, as we discussed earlier. But then this light emitted by the hydrogen gas passes through the outer layers of the atmosphere of the sun, for example, okay? So you have actually lots of gas, because this is the sun we are talking about, okay? So gas, then this gas, because it's dense and it has a lot of material in it, will emit a continuous spectrum, okay? So what do you mean by that? We will have some red over here, then maybe some yellow, then maybe some green, and maybe some blue, and then maybe some violet. Do I have violet? I do, okay. Okay, so this is what the situation will look like. Actually, this is gonna be continuous, okay. Oops. Actually, can I paint? Doesn't matter. Let's keep it like that. Okay. So then, what we will observe, because of the hydrogen, some lines here will be absent. Okay. So actually, no, this is not a good way to draw it. Maybe I'm gonna use a dark pen. Okay. So we will see something like this, lines like that. So these are the absorption lines. The black lines are the absorption lines. So if this over here was the spectrum of hydrogen or any other atom, then if we get the spectrum for that atom from the sun or other stars, etc., we'll see lines like that, okay? Those dark lines, okay? And why do we have those dark lines? Because those wavelengths are absorbed by the atoms of this gas over here, okay? And this is this everything I wanted to talk about? Okay, let me move on. Let's write a few more things. So in stars, actually, let's write this down. In stars, we have a continuous spectrum with absorption lines corresponding to certain atoms. Let's write it like that. Okay. Now, to go back to, I'm gonna switch on the air conditioning because it's really hot here in Cyprus. So let's go back to the star classification because this is the thesis of this video, I guess. So stars are classified into classes according to their temperature, oops, color, by color I mean the spectrum usually, radius, luminosity. Okay, and there is a table in your book. I'm not sure I can show that, but maybe I can search online. Give me a second, okay? Okay, here in Wikipedia, they list the class types. So you have the class O, B, A, F, G, K, and M. As you can see, the class O has the highest temperature. These are giant blue stars, okay? Their size is 6.6 times the radius of the sun or larger, okay? They also show the percentage of all, so I guess what they show here is that 76.5% of all stars are M class stars, and then only 0.00003% are class O stars. And they don't list here their lifespan, but the general rule is, like the saying goes in real life, the star that shines the brightest burns the shortest, something like that, I think is the quote. Meaning that large stars have so much material and so much energy that they burn through their hydrogen really fast, so they don't live too long. In your book, they say that their lifespan, their main sequence lifespan, is about 1 to 10 million years. We will talk about what the main sequence lifespan is. And if we check the class M stars, these have a surface temperature of 2000 to 3000 degrees Celsius. They are small, lesser than 0.7 times the radius of the sun. They are the most abundant. They have many molecules, as they show here, in their composition, and they live about 56 billion years. Okay, so these live for a long time. Okay, and these are red stars. They have the color there as well. So anyway, let's go back to the video. I mean to the notes. I guess when we talk about life in outer space, if there is any life in other star systems, then I guess the best candidate of a star is the M class because it lives for so long. So if a planet around can support life, that life will evolve and so on. So, and yeah, let's move on. Okay. Now, if we take the luminosities of the stars, if we take the luminosities of the stars from the table I just showed you, and their temperatures, and plot them against each other, against each other, we get the so-called Hertzsprung-Russell diagram. So let's plot. On the y-axis, we plot the luminosity over the luminosity of the sun, okay? And we use a log scale, meaning that each of these marks represents a jump of 10 in an order of magnitude. So 10 to the minus 6, 10 to the minus 5. Actually, let's do 10 to the minus 4, okay? So 2 jumps in the order of magnitude, 10 to the minus 2, then 1, so that's the sun, 10 to the 2, 10 to the 4, and then 10 to the 6. Okay, so these are the most luminous stars. But we will plot the temperature in reverse, meaning that temperature increases to the left, okay? So this is a peculiar thing about this graph, okay? So the temperature in Kelvin increases to the left. So we have the lowest temperature over here, 2500 degrees Kelvin, then 5000 degrees Kelvin, 10,000 degrees Kelvin, and 20,000 degrees Kelvin. Okay, you have hotter stars and you have colder stars as well, but we have to plot something, okay? Now let's use blue color to plot this diagonal over here, okay? Sorry, it takes some time. All right, this diagonal over here is called the main sequence. We will talk more about that in a moment, okay? Over here we have really, really hot stars in terms of temperature, but not very luminous. You see that their luminosity is 10 to the minus 5, the luminosity of the sun, so these are not really bright stars, okay? So these are the white dwarfs. Again, we will talk about this in a moment. Then all the way over here we have stars that are kind of cold but very luminous. So these are the red giants. And on top of this, we have even more luminous stars, which are also called, these are called the supergiants, super red giants. Okay, and actually, let's use boxes. So you have this class over here, this class over here, and then this different class over here, and then finally this class over there, okay? Now notice that there are way more stars, main sequence stars, that appear over here, like in the middle of this chart. So they have a luminosity of about 1, like the sun, and you don't have a lot of stars with a luminosity of 10 to the 6, okay? And this has to do with the abundance we talked about in the graph, okay? In the table, sorry, I showed you from Wikipedia. Really, really, really luminous and giant stars with really high surface temperatures and so on. They don't live for too long. They burn through their hydrogen fast. But we will talk about that in a moment, okay? Now, let's write a few notes about this diagram that's good to know. So, note. In general, luminosity is hard to determine. As here on Earth, we can only measure I, the intensity of radiation, which is measured by watts per square meter. So this is the letter I. I'm sorry for my bad handwriting, okay? And this is equal to the luminosity over 4 pi d squared, where d is the distance. So what am I talking about? Let's say we have a star over here in the Andromeda galaxy. No, that's a bad example. In the Alpha Centauri solar system, okay? So you have a star, but the Earth is over here, okay? It's a dot over here. So the luminosity is measured on the surface of this star, okay? But this star is at some distance d from the Earth. I think for the Alpha Centauri it's about 5 light years. I'm sorry for throwing around words that we haven't talked about yet. I'm going to talk about that in a moment, or maybe in the next video. But a light year is the distance that the light covers in 1 year, pretty much, okay? And I should remember it, but it's in the order of magnitude of 10 to 15 meters, I think. So it's a really large distance, obviously, okay? So here on Earth, we can only measure the luminosity over 4 pi d squared. Imagine how far away this star is, and then you take the square of that. So the intensity of light that we receive from this star on Earth is really, really tiny. Also, another problem is that we don't necessarily know the distance, okay? Or the distance might be really, really hard to determine. But anyway, assuming that we know that distance and we measure the intensity, we can find the luminosity by just cross-multiplying, okay? So that's important to know. I mean, it's not easy to obtain this Hertzsprung-Russell diagram, okay? It took lots of efforts by lots of astronomers to figure out this graph, okay? Another thing that is good to note is that imagine we found the temperature of the star using Wien's law. So this is something that comes up a lot in actual tests. So what do I mean by that? Remember that there is that curve, the Planck curve, the black body radiation curve. So this is it the intensity that we plotted earlier? Let me check. Yes, we plotted the intensity. Okay, so we have the intensity in watts in the vertical axis, and the horizontal we have the wavelength, and let's say we have a curve like that, and somehow we obtained this curve and we found that the peak lambda is red, so let's say 650 nanometers. Okay, so let's say that we had this curve in our possession. Using this, we found the peak lambda. Using Wien's law, lambda t is a constant. So using Wien's law, we can find t. So if we know t, we can actually use the Hertzsprung-Russell diagram to find the luminosity of the star, okay? So maybe the temperature was determined to be, okay, we said red, so it should be a very cold star. So maybe, okay, maybe this is the temperature of our star. And if we go to this diagram, we can find the luminosity, okay? And if we find the luminosity, we can actually find the radius of the star, okay? So that's kind of cool. Of course, okay, it can be a red giant, or it can be a main sequence star. But in general, we can use this diagram to find the radius of the star. And how can you do that? Okay, let's say we know the temperature, then we know that the luminosity is 4 pi r squared, because the area of the surface area of the star times sigma times t to the cube. Okay, so if we find the peak wavelength from the black body radiation curve, we can find the temperature, and if we find the temperature, we can actually find the luminosity from the graph, and if we know the luminosity, we can solve for the radius and find the radius, okay? Another thing to note about the HR diagram is that it is assumed, what's wrong with me? Okay, it is assumed that stars are black body radiators, and most stars, we already commented on that, most stars are in the main sequence. And just to give you an idea of what the main sequence is, and we will talk about this next, is that for stars in the main sequence, the energy from fusion counteracts the energy from the gravitational collapse. And what I mean by that is that in a star, you have a lot of material that presses inwards, right? Because the gravitational force is attractive, okay? So everything will collapse on a point if that star didn't produce energy from fusion to push this out and balance that, okay? So this is the energy from fusion, and this is the gravitational energy. Okay, now stellar evolution. That's the next thing we need to discuss, because I keep saying about the evolution of stars. We already talked about white dwarfs, etc. We didn't talk about them, we mentioned them. So let's go see what's going on. So stellar evolution. In general, stars are formed when nebulas which is hydrogen gas clouds. So this is what a nebula is. Nebulas are hydrogen gas clouds in space. So stars are formed when nebulas start collapsing. So this is a new iPad, guys, so I'm sorry, I'm still getting the hang of it. So start collapsing onto themselves. Because of gravity. So plain old gravity, okay? Let's say that we have some material of mass m1, some other material of mass m2 in this nebula, separated by some distance r. Remember that the gravitational potential energy between these two masses is minus g m1 times m2 over r, okay? So they are attracted to each other. Actually, before I keep writing things, let me show you. Let's go to Wikipedia again to see what a nebula is, okay? So nebulas. This is actually something I like doing when I teach, and I will try to do this in the videos as well, okay? Creating these videos is not easy, because in an actual class you have interaction with your students, which you kind of miss. So I feel like a crazy person talking to myself sometimes, but okay, I'm gonna try to make these videos interesting. So from Wikipedia, a nebula is a distinct luminescent part of interstellar medium which can consist of ionized neutral or molecular hydrogen and also cosmic dust. So nebula are often star-forming regions such as in the Pillars of Creation, in the Eagle Nebula, blah, blah, blah. I want to see whether they list like the size of these things. Actually, let's ask Google. So nebula's size. Okay, let's see. Okay, okay, they now have this AI overview, by the way. Google has that. I don't know how I feel about it, but it's mostly accurate from what I experienced so far. But anyway, so they can reach sizes of hundreds of kiloparsecs. We are gonna talk about that. A kiloparsec is about 3,260 light years. So yes, I was right when I said a few astronomical units. Actually, that's they are much larger than that. So these are huge concentration of gases, okay? And yes, I just wanted to have an idea about that, okay? Oops, no. How do I go back? Here, okay, great. Now, let's go back to this. Let's focus on this formula. So, S, the radius decreases, so as they come closer, pretty much, the GP converts to kinetic energy, which is simple to understand because, okay, I mean, if you have two static masses, M1 and M2, and they start being attracted to each other via the gravitational pull, then they will start having some kinetic energy, right? So the kinetic energy increases as the radius decreases, okay? Now, therefore, gas now has a higher velocity. Thus, it also has a higher temperature. Now, why is that? Recall that from the ideal gas law, 1/2 times the mass of a molecule times its average squared velocity is equal to 3/2 K times its temperature. So if we increase the velocity of the gas, we increase its temperature. I mean, it's plain to see, okay? Now, we start, let's summarize. We started with a nebula, okay, which started collapsing onto itself, and because of the gravitational pull, it starts having some velocity. Velocity translates to higher velocity translates to higher temperature. So what's so important about that? So when the temperature of this gas concentration reaches about 10 to the 6 Kelvin, and if the pressure is high, thus collisions between particles are more frequent, then fusion begins. Okay, and just to give you an example, the temperature in the center of the sun, so in the core of the sun, is 15.7 times 10 to the 6 Kelvin. Okay, and the temperature of the surface of the sun is 5,800 kelvins. Okay, just to give you an idea. So if we can imagine this as particles in a box, okay, gas particles in a box. As we increase the pressure, how can we increase the pressure? By reducing this volume, right? If we reduce this volume, these guys are gonna start moving faster. Therefore, because they move faster, they have a higher velocity, more frequent collisions. Therefore, fusion begins. Okay. And I have another note here in my notes. Let's write that. Let's write that down. So, another note. If temperature is 10 to the 7 kelvins, then the energy corresponding to that temperature, if we use the 3/2 kT law, ideal gas law, is 2.1 times 10 to the minus 6 joules. Okay? So if the radius of the nucleus is 10 to the negative 15 meters, and the charge of that nucleus is equal to 1 electron, then the potential energy is K. So what I'm trying to say is, not the radius, sorry. So actually, let me erase this. This is a signal that I need to edit out this part of the video. Okay, edit this out. Now, another thing I have in my notes is that if the temperature of a certain atom or nucleus is about 10 to the 7 kelvins, then this corresponds to an energy, if we use 3/2 kT, this corresponds to an energy of 2.1 times 10 to the minus 16 joules. If we have two such nuclei of charge E separated by some distance r, that is equal to about 10 to the minus 15 meters, then the potential energy, the electric potential energy of these two nuclei is K E squared over R. Okay, so this is equal to 2.3 times 10 to the negative 13 joules. Okay, so the electric potential energy is 1,000 times the kinetic energy of these nuclei. So what I'm trying to say is that if this nucleus is at a temperature of 10 to the 7 kelvins, it will have this much kinetic energy, and the same goes for this guy. But the repulsive potential energy due to their charge is 1,000 times higher. So how on earth do they fuse? Okay, this is a mystery. So this is not an A-level physics thing, but it's good to know so that fusion happens due to quantum tunneling. Okay, what I'm trying to say is that if nuclei were not quantum particles, you wouldn't have fusion, because the energies of these things do not allow for fusion to happen. So fusion happens due to quantum mechanics pretty much, but this is out of scope for you guys. So I just felt like it was cool to know, so I mentioned it. Okay, so this is the whole process. You start with a nebula, gas starts collapsing, the velocity increases, the energy increases, therefore the temperature increases. And when you reach some critical temperature, which is typically 10 to the 6, 10 to the 8 kelvins, fusion starts happening. Okay? And now let's move on. So we started having fusion. Now let's go see what happens with this thing. So there are two types of stars. So when it comes to stellar evolution, we generally deal with two types of stars. Those that have a low mass stars, which typically have a mass of about 0.1 to 10 times the mass of the sun, I think, and then high mass or massive stars. Both types start their lives as protostars formed during the collapse of the gas in nebulas and the ignition of fusion. When the energy from fusion, balances the gravitational pressure, the star enters its main sequence. Its main sequence phase. Okay, we already mentioned this, so again, let's use blue. So if you have a chunk of gas in a nebula, gravity makes it collapse onto itself. But once fusion starts, fusion actually creates energy that pushes this out, okay? So this is the fusion energy. If the fusion energy is exactly equal to the gravitational energy, then the whole system is at a balance that doesn't last forever, okay? But it's at the balance, and that balance is called the main sequence phase, okay? Okay. Now, do I want to mention anything else? No. Let's move on. So the whole process for a low mass star looks like this. Low mass stars lifetime. And by low mass, we actually mean that the mass, I said 10, but actually their mass is lesser than or equal to about 3 times the mass of the sun. I'm sorry about that. So you start with a protostar. Actually, you start with a nebula. Then you have a protostar, which means that you start having some fusion. Then you have the main sequence phase. Main sequence phase. Once hydrogen burns out, the star enters its red giant phase. I'm going to talk about that. The red giant phase. Then you have the planetary nebula phase. And finally, you have the white dwarf phase. Let me try to find something on Google about this. So let's actually use images. Okay, this looks promising. So they actually have all the phases we discussed. So you have a nebula, the gas starts collapsing, so you have a protostar. Once you start having some fusion, then gravitational pull keeps bringing the nebula together, and you have more fusion, and then you enter the main sequence. Then you, once hydrogen is burned out, you enter the red giant phase. Then it goes into the planetary nebula, white dwarf, and finally black dwarf. The black dwarf is when a white dwarf eventually stops shedding any light. So, okay, let's put the black dwarf here as well. I think the black dwarfs are hypothetical objects. They have never been observed, and I feel like even if they exist, it will be hard to detect them. But it will take the life of the universe is 15 billion years, so I think it takes 30 or 40 billion years to enter the black dwarf phase. Okay, I've read about it once, but anyway, you don't need to know that. So this is the lifetime of low mass stars. Now let's see what's going on with massive stars. These have a mass of larger than 4 times the mass of the sun. Okay, so again, we start with a protostar. Actually, with the nebula again. I'm sorry. I don't know why I keep forgetting that. So, nebula, protostar, main sequence, and the main sequence is also known as blue giant star. So, blue supergiant. Because they have so much energy, they are blue. Okay. Then once the material runs out, I mean hydrogen, they enter the red supergiant phase. So far, everything resembles the low mass stars, but let's go see what happens after that. So after the red supergiant phase, we have a boom. Okay, it explodes into a type 2 supernova. Okay, so then it can only go into 2 stages. So if the mass of the remaining core is larger than 3 times the mass of the sun, it becomes a black hole after the supernova. Okay, if the mass of whatever is left is less than 3 times the mass of the sun, it becomes a neutron star. Okay, so they go off in a massive explosion. Okay, and this supernova happens within a second, if I recall. So these stars, the giant stars, are kind of more interesting that way. So let's go find a diagram about, okay, let's go back to this and lifetime of a massive star. Okay, let's do that, of a massive star. Let me show you what's going on. Massive star. Let's use this, it looks interesting. So we start with a nebula. Protostar is when we start having some fusion again. The main sequence is when fusion and gravity balance each other. Then we get the red supergiant. By the way, notice how much bigger the star gets. And then we have a supernova explosion that leaves us with a neutron star or a black hole. Okay, let's go back to our notes and talk in a little bit more detail about all these stages. Okay, starting with low mass stars. So let's actually use blue. Low mass stars phases. Okay, main sequence, we mentioned it a lot. So we have hydrogen burning, and gravity equals fusion. Okay, once hydrogen runs out, a low mass star in the main sequence enters its red giant phase. In this phase, hydrogen in the core, so in the center, pretty much, in the core of the star, runs out. And helium-4, which is a product of the fusion, helium-4 sinks in the center, in the core. Why is that? Because it's denser, right? If you have gases, like if you have hydrogen gas mixed with oxygen, for example, oxygen is going to sit on the bottom of a bottle, for example, or of the atmosphere or whatever. Hydrogen is going to rise to the top because it's the least, it has lesser density, right? Like in liquids, like oil always sits on top of water because water is denser than oil, and so on. So the situation becomes as follows. So you have the helium-4 in the core, and you have, and we are talking about the red giant phase, by the way, okay? And you have hydrogen in the outer layers of the star, okay? And gravity keeps pushing on that hydrogen, okay? So that's gravity. So what happens is that gravity causes the outer hydrogen layer to burn, okay? This leads to a very small explosion, or maybe it's not good to think about it as an explosion. The whole thing enlarges pretty much, okay? So star enlarges. And also you have some helium-4 burning. So you have fusion of helium-4. When theoretically helium-4, if helium-4 fuses with helium-4, it can produce beryllium-8, okay? So, which is unstable, by the way, but whatever. So some helium-4 burning causes further expansion. And just to give you an idea, imagine that the sun is 1 astronomical unit, we are going to talk about that later, is 1 astronomical unit away from the Earth, okay? So it takes light that travels with the speed of light, 7 minutes to come from the sun to the Earth, okay? Which means that if the sun disappears, it's gonna take us 7 minutes to figure out. That's crazy. But anyway, that's not the point. Now, it takes, I'm trying to say that the sun is really far away from the Earth. When the sun enters its red giant phase, it is believed that it is approximate or speculated that it's gonna reach close to the Earth, so its surface is gonna come really close to the Earth, or maybe engulf the Earth, if I remember correctly. So it's crazy. It becomes really large. Okay. Okay, it stays in that phase for a while, and it forms a planetary nebula, which is their next phase. Okay, planetary nebula. So outwards expansion from the red giant phase makes the star to cool down. Okay, so, and also when the star enters its planetary nebula phase, some of the burning, like the hydrogen burning in the outer layers of the star, stops. And because it expands so much. It covers a larger surface area. It has a much large surface area, so it emits away lots of energy, so it cools down. Okay, and eventually we reach the white dwarf phase. So gravity, actually let me put boxes in these distinct phases. So in the white dwarf phase, gravity wins. Let's put this in quotes, and pushes the size down to a stable size. Okay. And what happens is that all white dwarfs in the universe have the same size. Okay. Electrons prevent, not the same, I think it's not the same. They have the same luminosity, but approximately the same radius or something like that. So electrons prevent further collapse. And this is known as a Chandrasekhar limit. Okay, so when we say gravity wins, we mean that we don't have lots of fusion anymore. Whatever was supposed to fuse fused already. So gravity pushes the star inwards. Okay, and gravity is counterbalanced by the electron pressure. This is how it's called. And what we mean by that is that, remember, inside atoms, we have the nucleus in the center and electrons orbiting around that, okay? So if we squeeze those electrons, okay, let's say we are dealing with an atom that has, I don't know, 2 electrons. So if you push them, they come close together, but remember the Pauli exclusion principle. Did we ever mention this? The general idea is that not 2 electrons cannot occupy the same orbital. Okay, this is something you probably know from chemistry as well, and because of that, a pressure is created by the electrons that prevent the total collapse of the star into a point. Okay, now massive star phases. Okay, and let's start with the blue supergiant phase, which is the main sequence. Oops, let's use red for the box. Okay, so we have hydrogen burning, but also heavy element burning, because these stars are so massive that there is enough energy to fuse helium-4, oxygen-16, and so on and so forth. Okay, up to iron-56. Okay, why iron-56? Because it's the most stable element in the universe with the highest binding energy per nucleon. We discussed that in the nuclear physics lessons. Okay, so the blue supergiant phase, which is the main sequence of massive stars, is slightly different but very similar to the main sequence of a low mass star, in that you burn hydrogen, but also you burn other things in massive stars. Okay, once hydrogen runs out, we enter the red supergiant phase, which means that hydrogen runs out in the core, and we have fusion or burning of heavier elements in the core, okay? The next phase now is the type 2 supernova. Okay, in this phase is that we have, remember when we talked about the red giant phase for low mass stars, we have burning of other elements, and this creates an outwards pressure that pushes gases away. But in the case of a red supergiant, eventually we have once, let's write this down, once we reach having lots of iron 56, the burning leads to an explosion which is violent with speeds of about 0.1 c. So 10% the speed of light. That's significant, guys. That's a lot of speed. Okay. And these events are crazy in the sense that we know of supernova that were visible, and we know this from history, like there was a supernova, I think about 1,000 years ago, which is reported in the writings of medieval civilizations in China, Europe, the Middle East, even the Americas, I think. And we know about these things. So these things shine bright for years until they go away. So these are that violent, okay? After this explosion, we have, if the mass of the remaining star is lesser than 3 times the mass of the sun, we get a neutron star. Why is it called a neutron star? Because remember when we said earlier that in white dwarfs, the gravity cannot push the electrons together, and the electron pressure prevents further collapse. In these stars, the gravity actually has enough energy to push the electrons onto the protons. To say, I mean, it's in some sense, this is what happens. So you have protons and electrons combining to form neutrons and electron neutrinos. Okay, so you have stars that are full of neutrons. Their radius is about 10 kilometers. So imagine how dense they are. You have 3 times the mass of the sun of material in a radius of 10 kilometers. So that's crazy. But if the mass of the remaining star is larger than 3 times the mass of the sun, then not even neutron. Actually, in neutron stars, I forgot to mention that the neutron pressure prevents further gravitational collapse because, again, no 2 neutrons can occupy the same state, just like the case of the electrons due to the Pauli principle. Therefore, the gravitational collapse stops. But if the mass of the remaining star is more than 3 times the mass of the sun, then nothing prevents it. So everything collapses into a black hole. Okay. And is there anything else I want to add here? No, except that I'm gonna go to this diagram of the luminosity over the luminosity of the, I mean the Hertzsprung-Russell diagram, okay? And this is the main sequence. So, and if we, over here, we're gonna have nebulas. Actually, let's put it here, nebula. So we start with a nebula, this is phase 1. We create a protostar, which is over here. And then the protostar collapses into the main star, main sequence star. So this is phase 2, phase 3. Then we go to the red giant phase. which is number 4, and then eventually everything collapses to a white dwarf. And this is for low mass stars, okay? So this is stage 5. Okay, and one more thing is the type 1 supernova that we haven't mentioned, because we said in massive stars we have type 2 supernova. What is a type 1 supernova? Okay, so this happens when you have a white dwarf near a star. Okay, so the white dwarf absorbs material. Actually, okay, let's write it down. White dwarf absorbs material from the star. Okay, if a critical mass concentrates on the surface of the white dwarf, so critical mass on the surface of the white dwarf, let's write it as white dwarf, okay, WD, then we have an explosion. And these type 1 supernovae are important to determine the distance to stars, as we will see in a later video. Okay, I'm gonna stop this video here, but because I wrote this down up, with whatever I had in my head, let's verify what I said. Let's Google it. So type 1a supernova is a kind of supernova that occurs in binary systems. Okay, I was correct. 2 stars orbiting one another, in which one of the stars is a white dwarf. The other star can be anything from a giant star to an even smaller white dwarf. Physically, carbon-oxygen white dwarfs with a low rate of rotation are limited to below 1.44 solar masses. Beyond this critical mass, they reignite and in some cases trigger a supernova explosion. The critical mass is often referred to as the Chandrasekhar mass. If a white dwarf gradually accretes mass from a binary companion or merges with a second white dwarf, the general hypothesis is that the white dwarf core will reach the ignition temperature for carbon fusion within a few seconds of initiation of nuclear fusion. A substantial fraction of the matter in the white dwarf undergoes a runaway reaction, releasing enough energy to unbind the star in a supernova explosion. So I was correct. Okay, it's good to check your facts, guys. I mean, even if you have a PhD, even if you are a full professor at Harvard, and hello to the to the physics professors at Harvard, even if you are a full professor, sometimes you have to check your knowledge because you forget things. But anyway, this is it for this video. Hope you like it. Let me know if these videos are useful in the comments, and see you in the next video.